So what I'm going to do here is, let's think about this for a minute. I'm going to put a plank here just like we did last class. So one end of the plank is supported by the scale, and the other end is supported by my hand, right? The plank is uniform, we can assume that. So how much is the force? Once I start the acquisition of data, what's the force that you're going to see in that plot? It would be the weight of the plank divided by 2, correct? That side is supports half of the weight. This side supports half of the weight because the weight of the plank is right in the middle. It's the symmetry of the situation, right? Two people holding on this plank, each person is going to do the same amount of force, right? It will be different, of course, if I move it this way. So that person, the center of mass will be closer to that person, right? That's equivalent to me walking on the plank, right? Getting closer to one of the supports. That person will be supporting more of the weight of the plank than I am, right? But that's not what I'm going to do. We already talked about that. What I'm going to do is take data of the force of on that side, right? And then I'm going to let go of the plank. It's going to be kind of loud, all right? And then what do you expect is going to be the force that the scale is going to show? Should it increase, decrease? Should it go immediately to 0? I mean, obviously, when the plank has left contact with the scale, the force should be 0. The scale is going to show 0. That is clear. The question is whether the reading of the force is going to go immediately to 0 from being half of the weight of the plank, or if something else is going to happen in between. So it looks like half of the weight of the plank is 14 newtons, so the weight of the plank would be 28 newtons. Close to 30. All right, so would you hold this for a second while I start it? So it's taking data. So it went to 0, right? But there's something else going on there. You spot something there? You? What is it? A little shoulder there, right? This thing. Let's zoom in. Oops, that's not what I wanted. There you go. So it looks like the force before I let go of the plank was 15, about 15 or 14, whatever it was, half of the weight of the plank. But there is a moment in time, maybe 0.2 seconds, 0.3 seconds, where the force is half of that. Where is that coming from? Let's start by asking the question, should the force of the scale drop immediately to 0 while the plank is spinning, rotating this way? Let me do it in slow motion. So I let go of the plank, so the plank starts here, and then the plank, because of the weight acting here, there is a torque on the plank. That doesn't do torque, that force. So the plank starts to fall this way, to rotate this way, right? But then at some point, the plank is going to slide. And that's when the force becomes 0. But while it's rotating, the force is not 0, right? While the plank is touching the scale, the force cannot be 0. There will be some angle there at which the force drops to 0, right? But what we want to understand is why is the force of the scale half while the plank is touching it but rotating? Why exactly half? That seems a very intriguing result there. So that's the scale. And here's the plank. Weight of the plank acting here. That's the force of the scale, right? And the initial situation was I was holding this with some force that was half of this, but then I let go, so that force goes to 0. Then we know that the plank is going to start accelerating, angularly accelerating, linearly accelerating also, right? Why angularly? Because there is a net torque here that is not balanced. So this force is going to make the plank accelerate with angular acceleration. Instantaneously, it's going to acquire some angular acceleration, right? How much is that angular acceleration? We could calculate this thing, right? Because the moment of inertia, we know what's the connection between the torque and the angular acceleration. We know that the net torque should be equal to the moment of inertia of the plank, but this is the moment of inertia of the plank with respect to this point, not with respect to the center, which might be what you find in a book, maybe. With respect to this point, the moment of inertia of the plank, this is going to be our pivot point, right? P. With respect to P, the moment of inertia of the plank is 1/3 of the mass of the plank times the length of the plank squared. Like I said, you don't have to memorize that. That's just a result I will give you, or you can find it somewhere if it's your homework. So times alpha, right? So alpha would be equal to what? The torque is due to gravity, and it has a moment arm. At this instant of time, the moment arm is L divided by 2. That's the torque acting on the plank. This force does no torque about P, and I have to divide by the moment of inertia of the plank, which is, did I call it capital M? Let's do it capital M. 1/3 of mL squared. The mass of the plank seems to cancel for the acceleration. One of these L's would cancel with that L. So this is 3/2 of G over L. The sign, what about the sign? Clockwise, so I need to put a minus for the torque, and that minus is going to be in the acceleration also. So let me write it on the bottom. So the acceleration is going to be minus 3/2 of G divided by L. Right? Okay, so that's one result. We're almost there. Side note here, notice that the acceleration of this end of the plank is bigger than G, because this point has an acceleration, linear acceleration of alpha times L. Alpha times L is 1.5 G, so this end of the plank is accelerating faster than the acceleration of gravity. So that was that equation, and we finished the calculation of this, trying to find out how much is F1 by looking at the second equation that says the sum of the forces acting on the plank should be equal to the mass times the acceleration of the center of mass. The forces acting on the plank are the scale, so it was on the other side, but F1 is the force of the scale, up, of course, to hold the plank, otherwise the plank would just go through the scale, minus the weight of the scale, minus the weight of the plank, and that is equal to the mass times the acceleration, Newton's second law. So that tells you that the force of the scale should be equal to mg plus ma center of mass. So still don't have an answer for F1. We cannot leave F1 in terms of the acceleration of the center of mass because we don't know how much is the acceleration of the center of mass. We're looking for a result for F1 just in terms of the mass of the weight of the Planck. So what's the next step? We know how much alpha is. If we could relate alpha with the acceleration of the center of mass, we'd be in business, right? Because we could use that equation into that equation, and then F1 would be in terms of the weight of the Planck. That would be it, and the length, and so on. Maybe. So, constraint equation. The relationship between alpha, the angular acceleration, and the linear acceleration of any part of an object that is spinning. What is that connection? We're looking at the acceleration of the center of mass, not any point, but in particular this point. That point has some acceleration. If the whole Planck is moving with an angular acceleration alpha, right? This point has a linear or tangential acceleration, as we called it before, right? Which will be equal to what? The normal or the usual connection that we have between tangential acceleration and angular acceleration is through the definition of radians, angle in radians, right? Do it here. If an object moves through an angle in radians theta, and that arc has a radius r, this distance s is r times theta, right? That tells you that the tangential velocity of an object moving in a circle is equal to r times d theta dt, r times omega. If you have an angular velocity this way, your tangential velocity has to follow this equation. Your angular velocity times r is your tangential velocity, your velocity. You don't have any other one if you're following a circular trajectory. And from this equation follows your tangential acceleration is equal to r times your angular acceleration. So if this point was accelerating as it moves in a circle, if it was linearly accelerating, that linear acceleration will be connected with the angular acceleration through this equation, right? The point that we're interested in is the center of mass, which is right in the middle of the Planck. The location of that point is L divided by 2 from the point of rotation. So what does that tell you about the acceleration of the center of mass as a function of alpha? Correct. Times L over 2, and then we can replace alpha, exactly. So, because of this equation, we can say, raise here, that the acceleration of the center of mass is equal to alpha times L over 2. Correct? So alpha is that thing over there, up there. So the acceleration of the center of mass, it's going to be alpha is minus 3 over 2 times g over L multiplied by, this is alpha, right? L divided by 2. So the acceleration of the center of mass is L cancels L minus 3/4 of g. So at that instant, when the Planck starts to go down, the center of mass of the Planck is accelerating down with only 0.75 of g. Not the full g, but only 75% of g. What does that tell you about F1? F1 must be slowing down the motion of the center of mass. If So I know that the center of mass of the object is going down with acceleration not g, but 0.75 of g. That means that something is working against gravity. That something can only be F1. There's no other forces acting on the plank. Correct? So F1 is going to have to be a quarter of mg. Right? Just take this result. We got the acceleration of the center of mass is 3/4 minus 3/4 of g. That minus is very important. So this is mg minus 3/4 of m times g, right? That gives you 1/4 of mg. And there you have it, the result that we measured experimentally, that little shoulder in the plot.